Hi, my name is Shivani Muthukumar and my project is doubling the cube. Geometry has been studied for thousands of years. It's one of the oldest, interesting, and impactful branches of math. In high school math, we learned geometric constructions that can be done by using a straight edge and a compass. We learned to draw lines and shapes using a line connecting 2 points, drawing a circle using a compass with a given point and radius, bisecting an angle, and drawing perpendicular lines. These constructions are done using a straight edge and compass and are done in a sequence of steps. In math, the definition of an axiom is a statement that is taken to be true, so further reasoning can be done. For example, if A and B are two numbers that are the same, and C and D are also the same, A plus C is equal to B plus D. It is one of Euclid's axioms that were made 2,000 years ago. There's a list of axioms that consist of geometric constructions that can be done using a straight edge and a compass. From that list, we can also find things that are impossible to do using a straight edge and a compass. Some examples are doubling a cube, trisecting an angle, and squaring a circle. In this video, we'll focus on doubling the cube, also known as the Delian problem. We will discuss its background, why it's considered impossible, and how origami can solve the problem. History. Doubling the cube is an ancient geometric problem and has an interesting story. According to Greek legend, Athenians were suffering from a plague. The Athenians asked the oracle for guidance on how to please the gods and stop the plague. The oracle told the Athenians to double the size of the god Apollo's altar, which was shaped as a perfect cube. So the Athenians doubled the size of the length, doubled the size of the width, and doubled the size of the height of the cube. But the plague continued. Well, the oracle told the Athenians to double the size or volume of the cube, not the linear dimension or scale. The new altar was 8 times bigger than the original and not what the gods wanted. So what were they to do? So here is a photo of the Delian problem. The Athenian solution is on the left, where they made the volume 8 times bigger and the side was equal to 2. The correct solution would be to make the volume 2 and the side the cube root of 2. Why is it impossible? Let's say we have a cube with the height of 1, width of 1, length of 1, therefore a volume of 1. If we wanted the volume of another cube to be 2, which would be double, the length of a side would have to be the cube root of 2. So x is equal to the cube root of 2, and x cubed is equal to 2. This becomes impossible to construct because the cube root of 2 is that number and is not a constructible number. According to the rational root theorem, we cannot solve this because the degree of the polynomial is not to the power of 2. So the cube root of 2 is not constructible. If the cube root of 2 is not constructible, the line segment can also not be constructed, and therefore the cube cannot be doubled. Origami solution. In the above section, we learned how the cube root of 2 is not constructible. In this section, we will show how origami paper fold can construct the cube root of 2. First, we need to get familiarized with origami axioms. Similar to how axioms based on a straight edge and compass were discovered, there are also origami axioms. The 6 original origami axioms were discovered by Humaiki Huzita. There's also a 7th axiom that was discovered by Koshiro Hattori. This addition was proven to complete the axioms of origami. The original 6 axioms are listed to the right with statements and images. The 6th origami axiom. The 6th axiom is, when given 2 points, point 1 and point 2, and 2 lines, line 1 and line 2, there's a fold that can place point 1 and point 2 onto line 1 and line 2 respectively. This is the axiom that will be used to solve the Delian problem. This fold of the 6th axiom is known as the Beelock fold, named after Margareta P. Beelock, who found that this origami fold can be used to solve the cubic equations in 1936. First, you have to fold a standard square piece of paper into 3 equal parts. The bottom corner, called point P in this image, is folded so that it's on the top edge. The crease mark on the opposite side must also meet the crease mark labeled Q. This fold results in the line PB being the cube root of 2 times the length of line AP. So PB divided by PA is the cube root of 2. Proof and explanation. So here we see a square sheet of paper with corners labeled A, B, C, and D. Here we see that point C has been folded onto point C prime on line AB, and point F has been folded onto point F prime on line GH. Here we call CB 1 and AC A. So a whole side on this square is A plus 1. And each third that was folded is A plus 1 divided by 3. So here we have point J, which is on line BC and shows the mark of the fold. And we call BJ B, and JC is A plus 1, so the whole side minus B. So to find segment GC prime, we have to do A minus A plus 1 over 3. So it would be this whole top section AC minus the 1/3. It's also written right here, and it is equal to 2A minus 1 over 3. Next, we know that C prime BJ is a right triangle. So using the Pythagorean theorem, we can say that 1 squared plus b squared is equal to a plus 1 minus b squared. And when you solve for b, you get b equal to a squared plus 2a over 2 times a plus 1. Now, we know that angle FCJ is a right angle. And as it's mirrored to F prime C prime J, it is still a right angle. So this angle right here, the right angle, and this other angle is equal to 180 as it forms a straight line. So if we subtract the 90 from the right angle, we can call this angle alpha and this one alpha prime. So here in triangle C prime BJ, we know that the angles are equal to 180, and this right angle also takes 90, and this here is alpha prime. So that means this is equal to alpha. Similarly here, there's another right triangle with a angle of alpha. So this one would be alpha prime. So now we know that these two triangles are similar, and similar triangles have sides in proportion. So for this triangle, if we take side B over the hypotenuse, a plus 1 minus b, and set it equal to segment GC, which is 2a minus 1 over 3 over the hypotenuse, a plus 1 over 3, those proportions are equal to each other. And so now we substitute B for the equation with A. So anytime there's a B, we're going to substitute it with this so that we can solve for A. And solving for A gives us A cubed equal to 2 and A equal to the cube root of 2. That is the result, and that is how origami can solve doubling the cube. A simple paper fold based on the 6 origami axiom allowed us to solve this impossible geometry problem. There are other quote-unquote impossible geometry problems that can be solved using origami folds as well. I found this learning process to be very fun and enjoyable. I learned about origami axioms and tried to fold them as well. The history of the Delian problem was very interesting, and I was excited to see all that math and origami share. I hope you enjoyed the information too. Thank you.